Hello, everyone. My name is Luning Zhao. Welcome to today's lecture. So in today's lecture, I will discuss basic concepts and principles of quantum chemistry, along with classical and quantum algorithm that could be applied to solve quantum chemistry problems. So why is chemistry so important? Because chemical reactions are happening everywhere 24 hours a day. So without chemical reactions, we would not have batteries that powers our phones, drugs that cure diseases, and trees that transform carbon dioxide to oxygen. Even light itself is built upon countless of chemical reactions. Okay, showing here is what's happening inside an organic solar cell. So it contains an anode and a cathode, and in between them are electron donor and acceptor materials. So photons will come in and generate the bonded electron and hole pairs. So they're bonded because the negatively charged electrons and the positively charged holes attract each other. The electron and hole pairs will then evolve in time, triggering many interesting things. For example, on the top here, it shows that they might recombine, the electron hole pair might recombine and emit a photon out. They might also, on the bottom here, they might also migrate to the surface. And once they reach the surface, charge separation happens and they become unbonded. The electron will then diffuse all the way to the cathode and the holes will diffuse to the anode, generating currents. So in order to develop a material that makes this whole process more efficient, we will need to have a very deep understanding of the electron's behaviors, such as how much energy does a photon need to form this electron hole pairs, and then how the electron hole pair will evolve in time, etc. And this is what quantum chemistry wants to answer. So another example here is artificial photosynthesis. So undoubtedly, climate change is a problem featured by all humans. For example, on the right top here shows a picture that looks like it is taken on Mars. However, this is San Francisco in last July. The orange looking sky is due to the gigantic California wildfire that put tons of dust into the sky and blocked sunlight. For me, it was just a few days of bad air quality, but there are people who lost their homes due to this. So artificial photosynthesis is one way to reverse the climate change. So by developing such a material showing the middle that once it absorbs a photon and generates these electron and hole pairs, the electron and hole could then diffuse to the surface of these materials. And in the meanwhile, for example, carbon dioxide molecules could also migrate to the surface. And once they meet at the surface, chemical reactions will happen, and the carbon dioxide is then reduced to carbon monoxide and hydrogen. So as one can see, in order to develop such a materials, one need to understand the behavior of both electrons and nuclei. Okay, now let's discuss what quantum chemistry is. On the very top level here, we have chemistry problems, such as how to develop efficient solar cells, how to design more novel materials, and how to develop drugs. To solve these problems on one lower level, it amounts to predicting certain chemical properties, such as how much energy it takes to cross certain reaction barriers and to what direction the molecule moves. And these problems are further driven by the behavior of electrons and nuclei, which are then governed by quantum mechanics. Finally, in order to simulate electron and nuclei on a computer, we need to develop programmable mathematical models that are based on quantum mechanics. So going from the lowest level of programmable mathematical models to the top level, where there are chemistry problems, is what quantum chemistry is trying to do. So we develop mathematical models based on quantum mechanics in order to solve chemistry problems. Okay, so fortunately, people have actually found the equation that governs electron and nuclear behavior 100 years ago. It is the Schrodinger's equation. So it has, for the Schrodinger's equation, it has a time-independent and a time-dependent form. For the time-independent form, we have the Hamiltonian, h here, acting on the wave function psi, which then gives you the energy of the system multiplied times the wave function. Here, the little r represents electron positions and the capital R represents nuclear positions in Cartesian space. So in molecules and in materials, for example, on the right here, electrons will form the discrete energy levels. Showing on the right, is a schematic plot of these discrete energy levels. And without external perturbation, they tend to stay in the lowest energy state. Under external perturbation, such as light absorption, they could also be promoted to high energy states. And solving the time-independent Schrödinger's equation tells you what the energies are of these energy states. So the time evolution of a quantum state is driven by the time-dependent Schrödinger's equation. Here, we have the time derivative of the wave function, which is equal to which can be computed by the Hamiltonian acting on the actual wave function. On the bottom here is an example showing how nuclei could move. In this molecule, the molecule as a whole could vibrate, and this particular proton marked in red could also transfer from the donor atom to the acceptor atom. So these are both accompanied. These processes are both accompanied by electron moving in real time, and they are driven by the time-dependent Schrödinger's equation. As we can see, the Hamiltonian is perhaps the most important quality in quantum chemistry and quantum physics. For an electron nuclear system, such as a molecule and a solid, this Hamiltonian could be written as this. So it contains, this Hamiltonian contains the electron kinetic energy, the nuclear kinetic energy, the nuclear electron repulsion energy, the electron nuclear attraction energy, and some time-dependent external field. Here, I would like to make an approximation, and it's perhaps the most important approximation in quantum chemistry, the Born-Oppenheimer approximation. So since the nuclei are much heavier, they're usually thousands or tens of thousands times heavier than electrons, we can consider them as fixed parameters. Then the terms in the Hamiltonian that solely depend on the nuclear disappear. And then what we left are the electron kinetic energy, electron repulsion energy, and electron nuclear attraction energy terms. So by solving this electronic Hamiltonian given fixed nuclear positions, we are able to obtain the electronic wave function that decides the motion and the behavior of electrons in the system. However, one needs to keep in mind that the Born-Oppenheimer approximation is not always valid. So this is in general true in quantum chemistry. When you make approximation, there will be cases where the approximation is valid. There will also be cases where the approximation breaks down. For cases such as the nuclear moves really fast, for example, if two molecules collide, when they move very fast, we could no longer treat the nuclei as fixed quantities, and the Born-Oppenheimer approximation will break down. All right, so now let's solve the electronic wave function, and the strategy we use is to guess. Suppose we have an n-electron system, and one particular guess would be for the wave function to have the product form. In such a form, each electron is described by its own function, and these functions are called orbitals. And the total wave function is the product of all of these functions and all these orbitals. However, doing so, approximating the wave function in this product form breaks the particle symmetry. So electrons are fermions, and for fermions, if one exchanges the position of two particles, the wave function picks up a negative sign. It is obvious that this product form of the wave function does not have such a symmetry. So in order to conserve the particle symmetry, we anti-symmetrize the product wave function. The resulting wave function is a determinant of this particular matrix. And as you can see now, for each row of this matrix, we have one orbital. And for each column of this matrix, we have one particular electron. So since exchanging two electron positions now becomes equivalent to exchanging two columns of this matrix of the determinant, which then picks up the minus sign due to the properties of the determinant, we have now restored the particle symmetry. Okay, now let's introduce another important concept in quantum chemistry, the basis set. So far, we have not discussed what these orbitals, this psi of k, should look like. So one choice is to expand them by a linear combination of a set of known functions. These known functions are the basis functions, and the particular choice of these known functions is called a basis set. And one common choice of these basis functions, of these known functions, is to use hydrogen-like orbitals. Showing here on the left is the 1s, 2s, 2p, and 3s, 3p orbitals of the hydrogen atom. Mathematically, they can be represented as here as normalized Gaussians multiplied by some polynomial. So Gaussians are handy choice here since electrons should be around nuclei due to the Coulomb attraction. Other choices also exist in quantum chemistry. For example, in material science, plane waves are usually used. And it is important to note that the more basis functions used to span these orbitals, the larger amount of space that these basis functions will span, the more complete the space will be, and the more accurate the approximate wave function will be. All right, so the next thing we need to do is to actually solve for the basis function coefficients. Here, a concept called the variational principle is extremely important. The mathematical form of the variational principle is shown here. It shows that if one computes energy in such a way for a gas wave function, that the gas wave function is usually called an ansatz, the resulting energy should be lower bounded by the exact ground state energy of the system. Therefore, finding these expansion coefficients C could now be transformed to an optimization problem that finds the global minimum of this energy. And then the lower one goes, the more accurate the predicted energy is, since the variational principle forbids one to go below the exact ground state energy. So based on the variational principle, the workflow of finding the best approximate wave function of a single determinant looks like this. So the very first step, we guess a set of coefficients C. Presumably, we can start from all zero of C. And then we compute the energy based on these guessing coefficients, after which we find the parameter change delta C that lowers the energy. This could be done by some optimization techniques, such as gradient descent. So delta C tells us to which direction the current guessing coefficient needs to change so that the energy could be lowered. Therefore, with delta C, we could update our guess of the coefficient. And then once we have updated our C, we can recompute the energy. This is done for many iterations until the energy stops changing or delta C becomes zero. By then, we claim that the global minimum of this energy has been found. So this whole process, guessing a C, compute energy, find delta C, update C, go so on and so forth, this is called the Hartree-Fock method, which is perhaps the cornerstone of quantum chemistry. Nearly all quantum chemistry simulations start from a Hartree-Fock calculation. We will see it later how it could be used in quantum computing. However, so after these amounts of efforts, the Hartree-Fock wave function that we have obtained is not a particularly good one. So in order to understand why Hartree-Fock wave function is bad, so let's consider a system where we have n electrons and n basis functions. Well, the Hartree-Fock wave function predicts the wave function to be a single determinant, with the first n orbitals being occupied, which is indicated by 1 here, and the rest n minus n orbitals being unoccupied, which are indicated by all of these zeros here. So on the right here shows a system where there are 4 orbitals and 2 electrons. So this is a configuration of Hartree-Fock in which the first 2 orbitals are occupied and the second 2 orbitals are empty or unoccupied. However, you will also note that this is not the only configuration for the Hartree-Fock configuration. We could generate other configurations as well by removing electrons from the occupied orbitals and putting them into the unoccupied ones. So for example, for instance, here are 2 examples of these different configurations than Hartree-Fock. The first one has 1 electron being promoted from the occupied orbitals to the unoccupied orbitals, and the second one has 2 electrons being promoted. So here also shows a schematic picture of these 2 configurations. In fact, all of these configurations would contribute to the energy. So in total, one needs to choose n from m orbitals to occupy, and this gives total of m choose n total number of configurations. When n and n becomes large, this quantity scales exponentially with the size of n or n, and there's no classical computer that could be used to solve this problem because the memory's need is so large. All right, so decades of research in quantum chemistry have come up with many classical ways of fixing Hartree-Fock. So first, we can write down the exact wave function, psi here, as the linear combination of all of the possible configurations given the basis set. And this is called the full configuration interaction, short for full CI. And we can write the Hartree-Fock term as a leading term with coefficient C0, followed by 1 electron promotions, 2 electron promotions, perhaps 3 electron, 4 electron, etc. So people have done many calculations using Hartree-Fock and then with this full CI expansion, and they have found that although Hartree-Fock is not the full picture, it is very close. For most cases, C0 is more than 50%, is more than 95%. So Hartree-Fock accounts for the majority of the wave function, and the rest small stuff could be recovered with perturbation theory. And people have developed many different flavors of perturbation theory, such as the molar placid perturbation, second order perturbation as MP2, and couple cluster, etc. However, so there are still cases where Hartree-Fock fails to account for the majority of the wave function. For example, in transition metal catalysts shown here, and in high temperature superconductivities. And when this happens, the perturbation theory will break down, since what's missing now is no longer some small stuff, but rather a large part of the wave function. So far we've discussed the quantum chemistry problems, Hartree-Fock method, and then classical ways of fixing Hartree-Fock to get higher accuracy. So I would like to pause here to see if there are any questions.
So the question is, could you please explain once again what the cats and the added as perturbations, the meaning of those terms?
I'm sorry, which terms?
I think all the cats except the Hartree-Fock. So those the perturbation cats.
You mean these
in the equation,
like the exact wave function expansion? The rest of the terms other than the Hartree-Fock?
Yeah, the meaning of those terms. Yeah.
Okay, so mathematically speaking, what these terms are, so they account for all these different configurations in Hartree-Fock. Suppose we have like this n orbital and n electron system. So Hartree-Fock is just one configuration where the first n orbitals are occupied and the rest are unoccupied. And then the rest of the terms accounts for the like these so-called excited determinants, where like certain electron has been promoted from the occupied orbitals to the unoccupied orbitals. And physically, what these terms mean is that they recover the so-called correlation between electrons. So Hartree-Fock kind of constrains the electrons to sit in certain orbitals. And then because electrons will repel each other, if they are not so happy of like staying close to each other, they will get excited to these high energy orbitals. So that's a fact of the electron-electron correlation effects. And then the rest of the terms accounts for these correlation effects.
So it's a question about when we use the variational method to get the ground state wave function. It seems that the optimization, it looks like the optimization problem in the quantum mechanics. Are there any approaches using the machine learning based, such as neural network?
Well, yes, there are definitely approaches that could allow you to use like neural network models. For example, so I talked about conventionally people have been using these Gaussian orbitals, like Hadron-like orbitals, to model the determinants. But in fact, you can also use a neural network model to model these determinants, because these neural network models are usually more flexible than just these Gaussian functions, and they tend to give you a more accurate wave function approximation.
Next question is, there are many kinds of bases. Is there ways or techniques to choose the basis set?
So yes, so which set of bases you use depends on the problems that you're trying to solve. As I mentioned, for molecules, Gaussian bases are usually the preferable choice, because it's correctly described that the electron cloud should be around the center of the atom, should be around nuclei, and should be decay exponentially as you move away from the nuclei. But in solid, because they form the electrons are more like uniform, so that in solids, because of the problems, people usually use, for example, plane waves to describe it. Because if you're trying to model the electrons, for example, in conduction band, It is more like a uniform electron uniform electron gas, in which we know the plan width is a good like basis to model that particular problem. So it depends on the problem you are trying to solve. Yeah, and I also want to add that, as I mentioned, although like these Gaussian bases are usually good for electrons, but they are also valid in certain cases. For example, if you do not have like external magnetic field, if you do have external magnetic field, you also need to change your Gaussian basis to conserve certain properties. And then people have developed a particular like basis set to tackle these problems. So you also need, the point is you need to change your basis because of your problems.
Thank you for the answering all the questions.
All right, so let's now discuss the quantum algorithm that could be used for quantum chemistry. Since we know that the exact wave functions are eigenstates of the Hamiltonian, with the exact energy being the eigenvalue, we could then apply the quantum phase estimation algorithm to find energy. So if we are able to prepare precise the exact eigenstate on a quantum computer and then implement e to the minus IHT as a quantum operation, the energy will be encoded as a phase, which could be then obtained by the quantum phase estimation. And then the question becomes, how are we going to prepare the exact eigenstates since we do not know it? And then how should we implement this U operator on a quantum computer? So before we go deeper, one observation that people may make is that the Hartree-Fock state, as we have discussed, is fairly easy to prepare on a quantum computer. All we need to do is to perform the X gate on the first n qubit and then flip them to the one state to represent the occupied orbitals, and then leave the rest n minus n qubits in the zero state to represent the unoccupied orbitals. This will help us later. Here, I will show the quantum circuit of the quantum phase estimation algorithm. So suppose we are able to prepare a certain or specific eigenstate psi n in the lower register. So in order to obtain the first 3 bits of the energy, we use 3 ancillary qubits. They are initialized in the zero state, followed by the Hadamard gate to put them in the superpositions. So we then perform the controlled U operation on psi n, controlled on the ancillary qubits. For example, after the case controlled U operation, the wave function of the case ancillary qubit becomes as this. As you can see, the phase has now been kicked back to the before the one state. After an inverse QFT operation, we could measure each ancillary qubit to get the phase and hence the energy. However, as we have noticed, we do not know how to prepare the exact eigenstate psi n on a quantum computer efficiently. So what will happen if we fail to prepare psi n, but instead prepare a linear combination that contains psi n with a coefficient of a of n? So in such a case, you can do some simple math, and it will tell you that after the measurement, the probability for the state to collapse to the psi m, the desired eigenstate, is given by am of square. So therefore, as long as a span is large enough, for example, as long as it is above 50%, we still have a good chance of measuring the desired eigenstate psi n. As you might recall, for the most cases, the Hartree-Fock states account for 95% of the wave function. So since we do know how to prepare the Hartree-Fock state, we can simply use this and then hope for the state to collapse to the exact eigenstate with a high probability. So now let's see how we can implement the U operator. In other words, how can we implement the Hamiltonian on a quantum computer? So here we need to introduce the concept of second quantization. In first quantization, the Hamiltonian is written in real space. A real space is defined by the electron and the nuclear Cartesian coordinates. However, this is not very friendly for written Hamiltonian in real space. It's not very friendly for qubits since Cartesian coordinates are continuous while qubits are not. So the first step is to transform the Hamiltonian into a different space so that mapping it to qubits is easier. So the way to go is to transform it into a second quantized Hamiltonian that lives in Fock space. Although I understand that the notation is a bit scary here, I just want you to believe that these two Hamiltonians are the same. So the Fock space is merely the space spanned by all the possible Slater determinants for an n-electron n-basis system. So within the second quantized Hamiltonian, the A and A dagger, the A dagger and A operators are called the creation and annihilation operators. So let's see what they do when operating on a single orbital. For the creation operator, if the orbital is unoccupied, it simply creates an electron in that orbital and makes it occupied. If the orbital is already occupied, it will destroy the state and results in 0. Since one orbital can only be occupied by one electron, the annihilation operator does the opposite thing. So finally, let's see how these two operators operate on a multi-orbital system. Not surprisingly, the creation operator destroys the states if the orbital is occupied already. However, if the orbital is unoccupied, not surprisingly, it creates one electron there. But in the meantime, it picks up an overall sign. Whether the sign is +1 or -1, it depends on the parity of the occupation. For example, if there are even number of electrons before this orbital p, the sign is +1. And if there are odd number of electrons before orbital p, the sign is -1. The reason that there is such a sign is, as you can guess, due to the fermionic particle symmetry. Okay, so now we have all the ingredients we need to map from fermions to qubits. What we need to do here is to map the creation and annihilation operators to Pauli matrices. So since we know what these two operators do when they act on a single occupied or unoccupied orbital, we can simply write them in this way. As you can see, for example, for the creation operator, when this matrix is multiplied by the 0 state, it's flipped into the 1 state. And when it's multiplied by the 1 state, it produces a 0 vector. However, doing this simple transformation breaks the anti-symmetry relation between these operators, as shown that by switching P and Q for these two matrices, we do not result in a minus sign, which should be there for these operators. So in order to conserve the symmetry, the Jordan-Wigner transformation is developed to do this job. As shown here, instead of having only x plus iy or x minus iy, we also tensor product it with these Z matrices. This allows us to conserve the symmetry between creation and annihilation operators. So here I also have an example showing after the Jordan-Wigner transformation what the A1 dagger A1 should be. First, we plug in the Jordan-Wigner transformed form of the creation and annihilation operators. We then apply these properties of tensor product and rearrange terms, and then we expand the parameters and apply the properties of the Pauli matrices, and eventually it becomes 1/2 times 1 minus the Z matrix. You can try to work it out the math to convince yourself. So since the Hamiltonian is a weighted sum of the product of annihilation and the creation operators, after the Jordan-Wigner transformation, it becomes a weighted sum of tensor product of Pauli matrices, which could then be implemented on a quantum computer. So to be more concrete, here I show how to implement this one particular term of the Hamiltonian controlled by Ancela qubits. So in this circuit, Q0 is Ancela qubits, and the tensor product of Z1 and Z2 is shown here at this 4x4 matrix. As you can see, it does nothing if the qubit parity is even, and it picks up the minus sign if the qubit parity is odd. So therefore, the first step is to compute the qubit parity with a C0 gate, and then the parity is stored in Q2. For example, 00 becomes 00 state becomes 00 state after the C0 operation, and 0 is a parity stored in Q2. The 10 state now becomes 11 state, and 1 is a parity stored in Q2. So after the parity calculation, we perform the controlled Z rotation on Q2, after which we then undo the parity calculation to restore the initial state. In this way, we could implement this operation using 4 C0 gates. 4 because there are 2 C0s for the controlled RZ operation. So since the Hamiltonian is a weighted sum of these tensor product of Pauli matrices followed by the same logic, you can essentially implement all the terms in the Hamiltonian in this way on a quantum computer. All right, so now in this lecture, we have covered the basics of quantum chemistry and its application in quantum computing. This plot shows what we have discussed. So let's now answer any questions the audience may have before we do the demos.
We have a question. In the previous slide, what does it mean to calculate the parity? Could you explain once again?
So the parity means like in a bit string how many, like whether there are even or odd number of ones, or even or odd. This is the whether there are even or odd number of ones. So then for example, the first C naught here calculates the parity. If it's 0, 0, then it's even, and then the C naught does nothing. The second qubit is not changing, so it's still 0, which is parity 0, which is even. And then if the state is 0, 1, the C naught also does nothing, and then still the parity 1 is stored in Q2. And if it's 1, 0, the first state controlled by the Q1, it will flip Q2. Then because now we still have odd parity, it is stored in Q2. And if the state is 1, 1, still the second qubit is not flipped to 0 because now we have a even parity. It is stored in Q2. So that's what I mean by computing the parity using C naughts. And you can generalize this to like multiple qubits. If you have one more qubits, Q3, for example, then you need 2 C naughts to compute the parity and then storing the last qubit and so on and so forth.
And you have a question. Can you explain how 2 C naughts are used for control Z gate?
So I think, so it's Nan here. He might be able to illustrate it more.
I'm here. What's the question?
Yeah, so how so the control Z, so why there are 2 C naughts?
I did not follow that. What do you mean? Are you asking if you need 2 C naughts for a control Z?
Right.
The how is the question, yeah. How 2 C naughts are used for control Z gate?
Am I interpreting that?
Needed for control Z, right?
So I think it's control Z rotation, like controlled arbitrary Z rotation.
Oh, I see.
And the question is why it is that you need 2 C naughts, or
Yeah, why, how, yeah.
Oh. How do I explain this? Is there an elegant way to explain this? I don't think I know a way. Yeah, I don't actually know a pedagogical way to explain why it is that you need just 2 C naughts as opposed to more. One is likely insufficient, right? In the sense that you're trying to entangle 2 qubits to a non-fully entangling degree, and C naught essentially fully entangles 2 qubits. So you're going to have to do some entanglement and then do something and disentangle a little bit. So you need 2. Now, why can you get away with 2 and not 3?
Question is not why, but how. So.
Oh, well, I mean, a circuit. You can look up the circuit identity. That's the easy part. Yeah. To explain why it is that you can get away with 2 as opposed to 3, it's probably because control Z is a very simple 2 qubit interaction. So, yeah, I can provide you with a mathematical proof as to why it is that you won't really need it, but I'm not really sure that is appropriate for the talk setting like this.
Another question is, do you use QPE in VQE?
So I don't understand what do you mean QPE in VQE? So QPE and VQE are two different algorithms. So what QPE does is essentially it estimates the eigenvalue of some matrices, and this particular matrix here is being the Hamiltonian matrix. It does so in an exact way. If everything is perfect, if the gates are perfect, if we have enough qubits to implement the Hamiltonian, then we should get the exact answer to how many bits that you required. Then what VQE does is that it forms an ansatz, so like the Hartree-Fock ansatz, but it's much more accurate than the Hartree-Fock ansatz. And it tries to optimize that on the parameters in that ansatz in a sense that it is optimizing them so that it lowers the energy. And once you have reached global minimum, you claim that you have found the best or the optimal approximate wave function. So it is, in contrast to QPE, VQE is approximate. How accurate it is depends on your particular choice of the ansatz, and also depends on how robust your optimization is. So these two are very different algorithms to solve the quantum chemistry problem. All right, so let's just open up the iterative phase estimation notebook. Yeah, so in this notebook, we implement an iterative quantum phase estimation algorithm. So initially, we need to do some setup. So, for example, we need to install Qiskit if you haven't done so, and we also need to install Qiskit IonQ and some other extra dependencies which are optional. All right, so the question is, why do we really care about the iterative phase estimation algorithm, and what can you do with it? So the iterative phase estimation algorithm is just a variant of the quantum phase estimation. As we already discussed, it could be, for example, used in estimating the ground state energy of the Hamiltonian. So what is the difference between the standard quantum phase estimation algorithm and the iterative quantum phase estimation algorithm? So the standard quantum phase estimation uses m ancillary qubits to obtain the first m bits of the phase that you want to estimate. So the iterative version of the quantum phase estimation algorithm solves for one bit at a time, and therefore only one ancillary bit is needed at each iteration. By doing so, this greatly reduces the number of qubits needed to perform the algorithm. Okay, so now let's see how the iterative quantum phase estimation algorithm works. We're going to try to compute the phase of these, or compute the eigenvalue of this T gates. And the T gates can be written in this following matrix. Okay, so here for these matrices, it has two eigenstates. One is 0 and one is 1. And for this particular eigenstate 1, the eigenvalue is e to the I pi over 4. And then if you divide pi over 4 by 2 pi, it will tell you that the phase is actually 1 over 8. Okay, so let's just go through all of this. Yeah, so the first thing we do is to I would just explain is more of what I would just go through step by step of what the iterative phase estimation do. So the first thing is that we initialize the circuits. So the auxiliary or the ancillary qubits will be initialized into a superposition of plus state by a Hadamard gate, and the other qubits, so the state qubit, will be initialized in the eigenstates. Here is just one state. So suppose the phase that we want to estimate can be written in this form, and each of these phi here is either 0 or 1 as the very initial, and then there are n bits that we want to estimate. And the very first step, we apply the U operation to the 2 to the n minus 1 times. So after applying the controlled U operations for 2 to the n minus 1 times, the wave function becomes like this. And you see that we now have the phase kicked back to the 1 state of the ancilla qubit. And if phi n is 0 and the ancilla qubit is in the plus state, and if phi n is 1, the ancilla qubit is in the minus state, and the inverse Fourier quantum Fourier transform could tell them apart. So now we have basically obtained the least important bits of the phase. And then we do the second step to apply this controlled U rotation by 2 to the n minus 2 times. And then if you work through the math, you can see that the overall wave function becomes like this. So since we already know what phi n is, which we already computed the least important bits, we can first do a phase correction for the ancilla qubits, and then it gives you to this state. And again, this is either a plus or minus state depending on the value of phi n minus 1. And again, we can tell them apart by an inverse quantum Fourier transform. And we continue this process for each iterations. Eventually, we get all the bits of our phase. All right, let's go to the code. So here we this function does. I'm sorry. Oops. Okay, so this function builds the circuits for the for one iteration of the quantum of the iterative quantum phase estimation algorithm. So first, what we do is we apply the Hadamard gate on the ancilla qubit to put it in the superposition state, and then we initialize the state qubit to the eigenstate, which is 1 here. And then we apply the T gates, which is controlled U rotations, to our state qubits by 2 to the m times, which is m is given as a parameter for this function. And then after which we perform the phase correction and the inverse Fourier transform. Then we measure the ancilla qubit. So here shows the actual circuits. So we apply Hadamard gate and X gate, and then the controlled phase gate, and then the phase correction now is 0 because the input value for the correction is 0, and then Hadamard gate again, and then the measurement. Okay, so that finishes one iteration of the iterative quantum phase estimation algorithm. Let's now put them together. So here in this function, essentially, we do a loop over the number of iterations that we want to perform, or the number of bits that we want to compute for our phase. We start by construct the circuits, and then we run the circuits either on a quantum computer or on a simulator, and then we get the measurements of the bits, and then we store these bits, and then compute the phase correction based on our current information of the bits. Okay, so after we have done the iterative phase estimation algorithm and then have computed all the bits that we want, we can then reconstruct the phase with this function. Okay, so we have went through the algorithm and the implementation of the iterative phase estimation algorithm. Let's now run it on a simulator. So here the backend is provided as a simulator, and we run the IPEA algorithm for 5 iterations to get the first 5 bits. And then we print the computed eigenvalue, which should be 1/8 as expected. And we can also try to use different number of iterations and then plot the results as a function of number of iterations. You can see here, if you're using if you're not using enough number of bits, you get 0. And if you are using like exactly 3 bits, since 1/8 is 1/2 to the 3, you get the exact correct results. And if you continue to increase number of bits, the results does not change. All right, now let's try to run the same algorithm on the actual IonQ hardware. All we need to do is to change the backend from the simulator to QPU. So if you run it, the job will be queued for a while. And then since I have run it before, so mine says done. And you can see that because this circuit is simple enough So IonQ quantum computer is able to produce the exact same results and also the correct results at the simulator.
So I believe there is one more notebook. So why don't we just move on and just come back later? And if there's
Sure.
any question before we move on, we can wait for yeah, a little bit more question if there's any.
If you use QPE to do quantum chemistry simulation, what is the size of the material that you can deal with?
Okay, so yes, that's a good question. So it's for now, because QPE QPE needs a really long circuit to run, because you have to implement the e to the minus IHT, the Hamiltonian. And then the number of terms in the Hamiltonian grows as n to the fourth with the system size. And because our current hardware are noisy, so far I'm only seeing QPE calculations on simple like small molecules like water, like hydrogen, and I haven't seen like QPE algorithm perform for other larger molecules. And even for the small molecules like H2, the results we got for the QPE algorithm is still very far from what we needed for the result to be chemically accurate.
There's one more question about the how many digits we can get from QPE.
How many digits we can get? So I think for this particular problem, for the estimating the eigenstate, like the phase of the T gates, so it depends on like how expensive it is to implement one like this controlled U rotation. So then, for example, if one controlled U rotation requires like 2 CNOT gates, and then if you need like m bits, then you need u to the 2 to the n minus 1. You need 2 to the n minus 1 times 2 CNOT gate. And then depending on how noisy or how good or how bad your hardware is, you can basically estimate, for example, if you already have an error rate of your CNOT gate, you can estimate how many CNOT gate you can perform to get a fidelity above 50%. For this particular problems on IonQ computer, I would imagine we can get as many as 20 bits with a fidelity above 50%.
Sorry, the n was the system size?
No, n is the number of bits you want.
Okay. You have 2 to the n 2 cubic gates and you can do 20 bits?
No, not 20. So yeah, so if 20 is not, I don't think we can do 20. We can, so it depends. So I haven't worked through the math. So if you require like 10 bits, then that's how many CNOTs are there? So it's 2 to the 9 times the number of CNOTs you need to get to implement the U rotation, right?
Yeah, I think
And
5 is good, right?
5 is, yeah, at least we can do 5.
Sorry, 9.
Yeah, so you need to work. We need to work through the math to get.
But I think the point is all about the error, not just you can basically calculate the like many digits as you want, but
Right.
Yeah, if you want more precision, you need more accurate QPU, but that's not what we have right now.
Yeah. I think the right way to put it is that there's no limit on how many digits that you can go, because no matter how many digits you want, you only need one answer qubit, because we only estimate one digit at a time, one bit at a time. But then the problem is that if you go to if you aim for 100 or thousands of bits, and then the circuit gets really long, and then the error will dominant results, and you will get nothing but the actual noise for those many digits. And then for most of the problems, we do not need that many digits to get the accuracy that we desire.
Oh, sorry, I didn't hear the last sentence, please.
Yeah, so the point is that you can go as many digits as you want, but if you go to a large number of digits, then the circuit's length get longer and longer. Then the error will dominate the results. And then for those if you're aiming for 100 digits, maybe after 10 digits, you're getting nothing but noise. Yes, and for example, if you need to do some large calculation for quantum chemistry, even implementing one control U rotation for the Hamiltonian requires thousands of gates to implement that. And then in that case, with current hardware, we cannot even estimate one base accurately because of the noise of the current hardware.
Let's move on. And what about the status of the that queue? Is it done? If it's done, you can show us, but not sure.
Okay, so this notebook does not require you to run on the actual quantum computer, so there will be no queue. So what this notebook does is to actually implement or to actually use the orbit to qubit transformation for a chemistry problem. So we will learn how to transform an electronic Hamiltonian from orbital to qubit space through the Jordan-Wigner transformation and other transformations as well using Qiskit. And we will show that the original and the transformed Hamiltonian had the same eigenvalue, aka the same energy. Yeah. So the outline of the notebook is as follows. First, we define our molecule. In a sense that we define the atomic coordinates, the charge, the spin multiplicity, and also the basis sets. And then we build our molecular Hamiltonian. Then we diagonalize the Hamiltonian to obtain the lowest eigenvalue, which is the ground state. And then we perform the Jordan-Wigner transformation. And then we diagonalize the transformed Hamiltonian again to get the ground state energy. All right, so first, let's define our molecule. So the molecule will be a simple H2 molecule with 2 hydrogen, and then they are separated by 0.75 angstrom, with the basis we use here is the STO6G basis. And once we have defined our molecule and the basis, we can perform the Hartree-Fock calculation. And then after we have done the Hartree-Fock calculation, we can perform a full CI calculation to get the exact eigenstate by diagonalizing the Hamiltonian. And then we can then print out the lowest eigenvalue, which is the ground state energy. And we can see it prints out the Hartree-Fock energy, which is SCF energy here, and the full CI energy. And you can see that the full CI energy is much lower than the Hartree-Fock energy. Okay, now let's create the same molecule using the same basis sets, but now this time we do it in Qiskit. Okay, now let's print out the second quantized Hamiltonian of this molecule. Okay, the next step will be to transform the Hamiltonian using the Jordan-Wigner transformation. And then the transformed Hamiltonian is printed out, and you see it becomes a weighted sum of product of Pauli matrices. The Jordan-Wigner transformation is not the unique way to transform from orbital to qubit space. The other transformations could also do the job. An alternative choice will be the parity transformation. The parity transformation optimizes the encoding of fermionic many-body system by qubits in the presence of symmetries. And then this will eliminate redundant degrees of freedom in a way that preserves the simple structure of the system Hamiltonian with fewer qubits. And you can see it here after the parity transformation, we can print out the transformed Hamiltonian. It becomes very simple of 5 terms, and now we only need 2 qubits instead of 4. And because this Hamiltonian is so simple, we can essentially build this Hamiltonian by hand. Then we first define all the matrices we need. The identity matrix, the poly Z matrix, and the poly X matrix is all we need. With these 3 matrices, we could construct our Hamiltonian. And here, note that I have discarded all the imaginary part because they are essentially 0. And then the final step will be to diagonalize our Hamiltonian and then find these the lowest eigenstates. So the last thing we need to do is to add the nuclear repulsion energy, which is not included in the electronic Hamiltonian. And since it is Coulomb repulsion, it can simply be computed by 1 over the bond distance. And then we can now add back the nuclear repulsion energy and compare the results of the full CI energy. You see that these 2 energies match to 4 digits after the decimal points.
Thank you for today's lecture. Let's take some. Let's wait for some questions.
Question is, to install PySCF in Windows, do you need some additional procedures? Because he or she couldn't do pip install PySCF.
I actually do not know an answer to that question.
네, 모르신다고 합니다.
Let me do some research.
Yeah, I think we saw this issue before, and not sure.
Yeah, I'm not sure whether you can get away from it other than like installing a Linux on Windows.
So have you found that the Qiskit Nature library, is it handy rather than just doing everything by your hand?
Well, yeah, Qiskit Nature is handy in certain ways, but it's also like not optimizing some other ways. Yeah, for example, if I try to like implement the actual like control U rotation of some Hamiltonian, it does in a very like less optimal way. It's just controlling every single gate on the qubit, on the ancillary qubits. But in fact, that you only need to control like certain gates. For example, you first compute the parity and then do the rotation. You only need to control the rotation, not the parity calculation. But then Qiskit seems to control all the gates to the ancillary qubits, which then results in a really long circuit.
So does it allow you to like intervene the library and just like simplify the circuit by yourself, or there's no way to do that? It is very abstract.
I haven't dig that far.
Okay.
To see if there's a way.
Yeah. One question.
Yeah.
So question is how? Yeah. I can do that.
I'll do it. Okay, go ahead.
So what's the difference between QSharp and Qiskit? So I think QSharp is developed by Microsoft, right?
Right. QSharp is by Microsoft. Qiskit is by IBM. So
could you point out like what is the differences between them?
That a question I do not know how to answer because I haven't like used QSharp very much. I only use Qiskit. Maybe like Nam uses QSharp before.
No, I don't use either. I use my own.
Yeah, you use your own.
Right. So, QSharp is newer and just coming out. I've heard. It's hard to say. It's just a different language. There's also Google Circ. I think everybody needs to look at each language and make their own decision on what they like, what works for them best.
Yeah, and QSharp I think is based on C#. Well, Qiskit is based on Python. So if you are familiar with Python, then Qiskit may be more friendly. But But if you're familiar with C#, then that's,
Yeah.
you can use Q#, I think.
And there is a request, if you can share the slide notes first, if you can send me the PDF file of the slide notes, I can post it with the recording, if it is okay for you.
Yeah.
Thank you.
I think Mingyu has it.
The notebook?
No, the
The
slides.
slides? Oh, yeah. I have it, yes. Should I send it to Junbi?
Yes, please.
Okay, yeah, no problem.
Thank you.